¿Sí? Vale. It's going to... Okay. So welcome to the Peter seminar. Today we have Diego Torres, who most of you probably know. He has been the director of the Institute for a number of years. And now he's hopefully getting fun again with peer research and collaboration and all sorts of stuff. But anyway, he's still at the Institute. I just will go quickly for those that you don't know Diego, and there's new people here all the time. So Diego was born in Buenos Aires, Argentina. He studied, I guess, also your undergrad and your graduate studies at National University at La Plata on cosmology and astrophysics and extended theories of gravity. Then you took, Diego took several fellowships at the Astronomy Center of Sussex in the UK, has worked also in Argentina in the Institute for Radio Astronomy at Princeton University and Lawrence Livermore Laboratory in the US. He's been doing also some research stays abroad, International Center for Theoretical Physics at Trieste, Salerno University at Varonisi, Italy, I presume. And then in 2005, he moved to Barcelona, where he initially got more or less simultaneously the first Ramon y Cajal Fellowship and then an ICREA professor position, which is still holding today. I don't know the year when you became the director of the Institute.
2016.
2016. So since when he arrived, he basically started the group on high energy astrophysics. Let's call it this way. Your interest is in relativistic objects, extreme objects that also are related to theories of physics, where you can test them and you can both learn from the astrophysics and also about the physics. And he's published numerous papers, including in several high-profile journals, including, I think you have even a National Astronomy yourself.
Yes.
As a single author. This is quite a feat these days, publishing single author, especially in high-impact journals. And Diego received several awards from the Chinese Academy of Science, from the US, from Argentina, etc. So without more introductions, I think everybody is ready to hear what Diego has to tell us today.
Thank you. Thank you very much, Guilherme, for the kind introduction. Thank you very much to everybody for being here. A lot of people today. I'm very happy of seeing how many people are here just to listen what I have to say. So today the topic is pulsar similarity. The topic itself is kind of new in the sense that what we want to achieve is to understand what makes a pulsar similar from one another. And in this particular talk today, I will try to focus on this topic from the perspective of the pulsar light curves. Let me just, since this is a bit challenge, to introduce a little bit on. We tried everything except the moving of the slides.
Maybe the click. The click.
No. The click. Yes, the click works. So since this is a bit challenge, I was saying, let me just remind you that ICE, our institute, is a member of the Fermi-Large collaboration. Fermi is a satellite. It's a gamma ray satellite. It was launched in 2008. So now they are 17 years flying. It has no consumables. So we are fighting every year and a half, more or less, against what is called the senior review in the US in order to secure its continuance. And for the moment, this has paid off. And we are still accumulating data on, and this is very, very nice because the statistics with which now we can study known objects is very high. We can study also variability along more than a decade, but in addition, we are discovering objects and systems that at the beginning we are thought impossible to achieve because the sensitivity increases with time. Particularly above 1 GeV increases linearly with time. So this is not something to disregard. We have done a lot of things in Fermi. Since the very beginning, we have been involved in the what is called the bright source list and also the population associations. leading to the first and the second source catalog, and then the first, the second, and the third pulsar catalog. I will discuss this in more detail. We have been related with the pulsar wind nebula and with the supernova remnants catalog and with the first young and millisecond pulsar discoveries in Fermi. And then for particular systems, we have led the research and reported on the first discovery of gamma ray emission from a starburst galaxy from individual supernova remnants, the first detections of supernova remnants in GeV gamma rays, the first gamma ray binaries with orbital and superorbital gamma ray variability, periodic variability from precession of micro-quasar jets, and first upper limits on magnetar gamma ray emission. What we are doing now is more or less detailed here. We are looking for accreting millisecond pulsars. We are glad that hopefully at the end of the year we will have something to say. I am optimistic there. These have yet not been discovered in Fermi, and as a result of what I was saying before, now we have the chance to go after accretion processes in gamma rays. We are trying to enlarge the population of gamma ray binaries and also characterizing and searching the population for more members of the population of transitional pulsars. We are looking in detail to ICREA. Margarita, this is interesting for you for sure. We are analyzing diffuse emission in regions of nodes, particularly in the surrounding of magnetars, just trying to see where the magnetars itself can affect the surroundings, if close to molecular clouds, and things like this. And a lot of things related to the topic I am going to cover today, which is related to the third pulsar catalog and the interpretation and analyzing similarity. This is just a summary of some of the things we have done in Fermi. I put it there essentially to leave it there because this is a lot of text, but if you are interested in reminding some of the papers that we wrote, you can go back. What is the situation now in gamma ray? So this is a summary, very quick summary of what are the main input for information in for the gamma ray side. So you have something called the 4FGL and the 4FGL-DR4, which is like an extension of the 4FGL for Fermi source catalog. 4FGL is the fourth Fermi source catalog. And this is what you have in the 4FGL. So you have more than 7,000 sources now with more than 4 sigma. And then they can be divided in 3 parts, essentially 1/3, 1/3, 1/3, more or less. So you have some firmly identified sources. This is, let's say, is less than 1/3, is the smallest of the 3 in number, the less numerous class, let's say, in which essentially you have pulsars. And they are discovered because of pulsation. So you are sure that you are observing a gamma rays coming from a pulsar because you measure the pulsation, right? And you actually discover the pulsar in other frequencies, like in radio. In blue, you have a lot of sources for which we think that we know from where the gamma ray radiation is coming, and this is called associations, mostly blazars. So you see the distribution in galactic coordinates is consistent with that. And then you see black sources all over, but especially in the galactic plane, where most of the sources, or 1/3 of all the sources, 1/3 of all the sources at most of the sources in the galactic plane are actually unidentified. So we really don't know what they are. At the very least, we cannot be sure with the data at hand of an association. In addition of this, we have the gamma ray sky. This is called the 3PC, the third pulsar catalog. And if you go here, also below and before, if you go back, also there is a website where you can access all this information. And this catalog is very generous in information. Actually, everything is public here. So you can download all the data, all the ephemeris used in the detection, everything. You can download the light curve, and this is also online. And then The other things that is very useful is called the light curve repository. This not only includes the pulsars, but also any other source for which there is variability detected, and then the light curve contains some variability. So you can see, you click on one of the stores, and then you open up, in this web page, you open up, and you can actually see the light curve of along the 17 years of the Fermi-Large. So let me go back to the third Fermi catalog, and particularly focus on the light curves. The light curves are the most important part of the catalog itself. So we have 300 pulsars reported in the catalog. This has to be compared with the situation before Fermi was launched, where only 5 pulsars were known. Now we have more than 300 pulsars known, about 340 pulsars in total. And we have the 3PC light curve samples with different levels of precision, particularly because the flags coming from different pulsars are different. So the ones that are more luminous, you can have a much more detailed light curve. And in those cases, you can go up to 800 beams in phase. 800 beams in phase from 0 to 1, so from a whole rotation of the pulsar is a treat. Really, the error bar is extremely small, and you can, no theoretical model can compete with that level of observational detail. But in general, you can go from, there are a few that are not very well measured, in 25 beams only, but most of them have 50, 100, 200, 400 beams, which is quite a lot. So very detailed light curves are there. There are 2 related PhD theses in the making here. These are the persons doing the PhD, so recognition of what I am going to say goes essentially to them. And they have missions, right? So the mission, as I stated, if he chooses to accept it, which he did, is to dig out what makes a pulsar similar to another, find a more informative representation of the pulsar population, and quantify the similarity of pulsar light curves, understanding implication for the magnetic field. And then I stated that the institute would not be responsible, me neither. And for Daniel, the mission was to significantly improve our previously existing spectral model for pulsars and make it able to concurrently predict the light curves as well. So we wanted to have at the same time prediction for light curves and spectrum. We have some ideas of how to do this, but of course it was a mission impossible, no? And especially we wanted this to be a computationally limited cost. I mean, not take 4 years in order to see what were the feeds. So they are actually succeeding in this. So, and what I am going to say is contained, or is going to be contained partly in their thesis. So let me go directly to the first point of the talk, novel look at the pulsar light curve. So let's start from some examples of the 3PC light curve. So these are real examples of counts as a function of phase, pulsar phase in the rotation. And the idea is that these are single peaked, only one peak that you can see, okay, without having a very well stated definition of what is a peak. You can concur with me that here this light curve have only one peak. And these are examples, sample at different sizes, and also they have very different flags. The shape is also very different. And these are the things that you see when you download the third Fermi-Large catalog. Now, let's do the following simple exercise, which is, let's consider a transformation in which we transform the counts, we subtract the background. So these light curves, as also the background is given in the third Fermi-Large catalog, it's telling you how many, which is the background level of photon counting that you have in this direction of the sky. So we will subtract the background in order to focus just on what Fermi-Large believes is coming from the pulsar itself. And let's divide by the maximum minus this background. And the idea is that by doing this transformation, we will get rid first of this scale. We will map all the light curves between 0 and 1. And we will just focus on the morphology of the light curve. So we will just focus on how much different from the background it is at different phases. In addition, the phase itself is arbitrary, right? It's from 0 to 1, but you can start counting every repetition of the pulsar cycle whenever you like. So in principle, you can rotate these light curves as you want, and we will rotate them every beam. So we will rotate beam by beam, so to consider all rotation. So the idea is that phase is arbitrary, so rotation will be considered. We will map all the light curves in a range from 0 to 1 by removing the background, and we will emphasize by doing these two things the morphological difference. When we do this, what we obtain for the same light curves is this. So they are essentially the same light curve. Despite that when you go to the Fermi-Large light curve, they look, the Fermi-Large pulsar catalog, they look very different. When you do this simple transformation, they look essentially the same object. So let us dig in detail a bit more on this. Here we are reminding when this DAG appears that these are transformed by rotation, normalized, and background removed. Instead, in here you have no DAG, so these are Fermi-Large light curve as you find them. When you do the same operation with other set of light curves, for instance, these are examples. There are 300 of these examples, so I'm just putting here some examples. No? These are examples of with two peaks, right? So here you do the same operation, and of course, not all of them are the same. Again, here I'm going from 0 to 1, and we rotate them so as to seek for the best alignment. So you have some are similar, and some are not similar. Actually, what can happen is that here you have a different peak separation. The relative height between the peaks is different. For instance, look at the yellow pulsar here. You have this very different height. Instead, the red one is very similar heights in the two peaks. And the peak width here looks very similar, but the blue one is much smaller, for instance, than the green one. So they are not always the same. So this way in which we look at light curves, which is a lot depends on the eye of the beholder, right? So you see that they look similar or they do not look so similar. They have two peaks. Nobody really have a definition of what is a peak. It's at all not trivial because of many complications at the observational level. I will not enter into that, but you go to the catalog, it's much discussed there, but it's not trivial at all to define what is a peak and what is not a peak. And there is essentially no quantitative estimation of how much similar is a light curve from one light curve to another. So our aim was to try to estimate this. And the first thing you can do is to consider the Euclidean distance between two time series, two light curves. So this is a simple example in which you have two time series of 5 elements, and essentially you have one light curve in green here and another light curve in red, and you actually compute the distance. Since this is normalized counts, now you can actually do so because you have previously normalized the counts. So you can actually compute this matrix, and the matrix is the distance from one point to another. So for instance, 3 minus 2 is 1, 1 squared is 1, 3 minus 0 is 3, 3 squared is 9. So you can actually compute this matrix one by one. And then you can, for instance, consider the diagonal of this matrix that tells you which is the summation of all the blue connections here. And this is how far in Euclidean, in some definition of the Euclidean distance, is the green curve to the red curve. You can do so for all the light curves. there are certain things that you have to take into account. You can do that kind of thing whenever you have the same number of beams in the light curve, right? So one possibility is to consider, for instance, all light curves having 25 beams and compare one to another. I mean, all of them. So if you have, 25, you have 25 times 24 divided by 2 different situations, no? Because, a light curve, light curve A compared with light curve B, and light curve B compared with light curve A is the same distance. So you do this for 25 beams, 50 beams, 100 beams, 200 beams, 400, 800, whatever. And you see that this sort of similarity appears in all light curves, in all sets. So it's something that is underlying many different cases in the pulsar Fermi-Large pattern. No? Now, you can rebeam in principle. So if you have 200 beams, you can say, okay, let's consider all of them 100 beams. You lose part of the population because you can rebeam but not invent the data. If you have less beams, you cannot add just the data you like, but you can rebeam. No? But then you lose some information by rebeaming. And actually, you can prove by technical reasons, I can enter into this, that this is not the best approach you can think of. One reason that it's easy to understand is that similar light curves that are not precisely aligned, for instance, let's consider you have 2 peaks, and the 2 peaks have the same height in 2 different light curves, but they are not precisely aligned. Then the Euclidean distance will give you a very large distance, because when you have a peak in one light curve, there is no peak in the other, and vice versa. And this will always give you a large estimate. So they will be singled out as being very much dissimilar, when actually they are not. They are just, you have the same peaks, the same height, the same width of each peak, just the separation is a bit different. So you want to avoid these kind of things if you really want to look for similarity. And actually, there is something called dynamic time warping. This is a concept that is very much used in many other fields, but astrophysics. It is used to study heart diseases, for instance, to study how much different is the electrocardiogram in the heart from a person who has a disease with a person who has not. It is used in stock markets, just to try to see the evolution of the market in time and to make predictions using this. And especially it is used for speech recognition. For instance, one typical example is if I read a text at a certain velocity, I'm using my own voice, and someone else read the text at a different velocity, then in order to distinguish that we are playing the same notes, let's say, by reading the text, then you have to do some estimation of something that's called elasticity. So because you are reading actually the same notes or reading the same words, but at different speeds, happening at different times. So you need to warp this time, and this is called the dynamic time warping concept. It is an optimization method to compare time series. So we are going to use this from these other fields into pulsar astrophysics. It works by dynamically aligning the time series even when they have different sizes. So you get rid of the rebeaming issue by using this thing. And the goal is the optimization of the cost to connect all points that you have in the light curve number 1 with all points that you have in the light curve number 2. And this is called the optimal warping path. This all appears to be much complicated, but at the end, it's only computationally costly. It's not really that much complicated from a mathematical point of view. You have some conditions to fulfill. Essentially, they are the boundary conditions of the initial and the final elements of the time series must face each other. This for us does not represent any problem because we are going to rotate all the light curves in all the beams. So we are going to consider that all beams could be at the beginning or at the end. you have to respect what is called the monotonicity and continuity condition, which essentially means you are not allowed to jump back in time, so to change the order of the light curve, of each of the light curve. You are not allowed to jump back or jump forward in time. The resolution for this optimal problem mathematically can be written in this following way. So you compute all possible paths connecting the two light curves. I am going to give you an example now so that you see, and then you search for the minimum. So let me go to an example. For instance, let's consider these two time series here. The first one has only 5 bins, and the second one has more. And you construct this distance matrix between these two time series, similar as what I did before. So 3 minus 2 is 1 squared, 3 minus 0 is 3 squared. You construct this, and then you construct another matrix, which is called the cumulative cost matrix, through assuming each of these values. And then, for instance, if you are here, if you want this number here or here, which number 2, this 2 comes by assuming this one and taking the minimum of these 3 ones. So 1 plus the minimum of these 3, 1 plus 1 is 2, and so on and so forth. And the idea is that in order to reach to a given element in the light curve without jumping back and forward, you can only do so by going in this way, or by going in this way, or by going through the diagonal. So you compute all possible paths and finally choose the minimum. And this is what is called the dynamic time warping path. If you were to connect these two light curves, now this means that, for instance, this point here is connected with this one, the final one with the final one. This is imposed. But again, you are rotating all the light curves. So at the end, you test all possible combinations. And then here, you have this point connected with both this one and this one. This one is this one. So it's not parallel, right? So you are warping, you are deforming, you are elastically deforming your time series, trying to look for an estimator that searches for similarity. So this has several advantages, because this is, first, it is a well-known technique. I have no idea why it was never used in astrophysics, or not so much used in astrophysics, never used in high-energy astrophysics before. No idea, because it is used everywhere. So there is not much to invent at the technical level. It's very useful to find similarities in that are beyond the simple alignment that you see with the eye. Right? It associates morphological structures. So peak with peak. It doesn't mean that the peak and the other peak happens exactly at the same phase. You can associate peak with the peak that is close by. So it can be applied to light curves of any number of beams without rebinning, and provides at the end a number, which is the cost for the minimum path. And this can be used to actually quantify the similarity. So this is now using the DTW, the dynamic time warping values, where when you go to the 3PC, when you go to the catalog and you look at these light curves, you see that these are the shapes. Some are almost invisible to see because of the differences in weighted counts. For instance, this one compared with the blue one, it has 1,000 counts in a single beam, and this is maybe a factor of 3 or 4 more than the whole counts in the whole phase with this one here. But then, for instance, in this and this are also very different in flux. They appear to have all one peak, these two peaks. When you rotate, you background subtract, you focus on the morphology, and you apply dynamic time warping in order to look for the differences. These curves are the most similar of the sample. They, for instance, they look like this when you do this estimation and identify. For instance, in particular, these two are exactly the same light curve. It's essentially the same, only the flux and the rotation is changing. These are some other examples with very different curves as well, and you can see that they are very similar. Look at this, for instance. This one, if you compute this in Euclidean distance, they will say, I mean, the Euclidean distance value will say, well, these are very different because when you have a peak in the green one, there is 0 in the red one. So all this distance is very large. And vice versa, all this distance for the red to the green is very large. So the summation of this is going to give you an Euclidean distance that is very large and will never be identified by Euclidean distance estimator. And the eye will never identify any similarity here. However, they look quite similar, I would say. There is only this small difference. So we can actually quantify this because we have 294 CPC pulsars. That means that we have more than 43,000 comparisons. And then we can actually study the distribution. And the distribution is a Gaussian. And you can actually see that this is 1 sigma, 2 sigma, and 3 sigma level in how similar they are. So since these are values, you have the DT values. Inverse of that is how similar. The larger the inverse is, the more similar the light curves are. So you can actually say, well, use this as an estimator of similarity, because then I can associate a precise meaning. I can say that if I have a similarity of DTW, if I have a DTW in here, whose inverse is, I don't know, 3, then this is 5 sigma beyond the mean of the distribution of how similar the light curves are in the whole sample. So this actually permits to define intervals of confidence in similarity. This is completely new. And with the intervals of confidence, then you can cluster the population of pulsars. And this is how you can do it. For instance, these are graph representation. This is a graph representation. So every node here is a, let's focus on this. Every node here is a different pulsar whose light curve is more than 3 sigma similar in the sense that I have just explained to one another. So every edge here in green means that the light curves of these two nodes are 3 sigma similar or more, 4 sigma, for instance. And then you see this, and perhaps this is this. I will come back to it. So this is this class, right? What happens with the edges that are not connected here, for instance, from here to here? Does this mean that they are not similar? No, they are similar, but maybe at the 2 sigma level or 2.5 sigma level, so they are not. I'm just showing here the more than 3 sigma similar cases. So let me show this in more detail. For instance, this case is exactly the one that I was showing you. So you have 12 pulsars whose light curves are similar at or more than 3 sigma level in the sense that I have just explained. And this, you have another cluster, and you can actually build clusters of light curves in this way. Now, main message now. How do these pulsars relate to each other? Do they have something in common? And the answer is no. They have very different timing properties. They mix young with millisecond pulsars. They have very different timing-derived properties, such as, for instance, the spin-down power, magnetic field at the surface, or the magnetic field at the light cylinder. They have orders of magnitude of differences. They have different even spectral properties. So if you look at the spectrum, this can be different. So in general, there is no correlation between light curve similarity and similarity in any other magnitude we tried, and we tried a lot. We couldn't find any correlation. This means that geometry is ruling. This means that not only geometry is ruling, but essentially that all pulsars are governed by the same process with more or less a similar magnetosphere, independent of the properties of timing or timing derived. Okay, so now I mentioned related research. So let me just give an excursion to this. This is going to be an excursion because it would take too much time. I don't have so much time left. But we are studying this from the point of view of theory now. For many years, actually. We started back in 2019 with Daniele Vigano developing a novel way to describe magnetic line in a pulsar magnetosphere. And we did so using what is called the Frenet-Serret differential equations, which are this sort of equation here where you have a radius of curvature and also some torsion in the system to describe how the normal and the tangent of a particular line change along the curve. This is used for a lot of application in differential geometry, also in architecture is very much used. We built an emission region around a center value in magnetic colatitude by using these formulas here, which, if you look at the plot, is giving you a region such as this, which is very similar to what you obtain in particle in cell simulation. So the aim is to build an emission region with a realistic shape, which we did. And then this realistic shape is, as I said, inspired by particle in cell magnetic simulations. Consider trajectories of particles in this region. And at each point, consider the radiation emitted by these particles via synchrocurvature emission, which is something that Daniele, me, and some other people from out of the institute have introduced earlier, back in 2015. This synchrocurvature emission is at the same time the process that involves synchrotron and curvature, but not in a separate way, but together. This is a very versatile approach, and you can have very different emission regions, essentially changing 3 parameters. Actually, we have computed out of this what is called the emission, the sky map, or the emission sky map, which is essentially at a given energy in a given phase for a given observer, which is the count rate that you expect. So if you cut, this is on the sphere of the sky, and if you cut this for a particular observer, you obtain a light curve. We did this with only 6 parameters. 3 for the spectrum, where these are the previous states, let's say 2018, 2019, 2020 of our model. And we added this now, and we are now in 2024 and today, where we have inclination angle, meridional extent, so how is the width of the accelerating region, and which is the injection range, how large it is. So basically, a part of these 6 parameters, we have the period and the period derivative that are fixed for every single pulse. So we are able now to actually compute the sky maps, and we consider a lot of different light curves for a given pulsar just by varying these parameters. What we obtain, and this is a paper of the last months of last year, are this kind of things. So we obtain the sky, we obtain the region first, we obtain the sky maps, we consider a lot of light curves for a particular pulsar, and then we compare with real light curves. Like, for instance, you have 2 peaks, 2 peaks. So we are reproducing more or less the general features of the light curves. This is something that right now we are working at an individual level, just by fitting. We also reproduce at the same time the spectrum. So what we see is that for different observers, the difference in their spectrum is much smaller than the difference in their light curve. So essentially, basically changing the geometry, you change a lot the light curve, but you don't change so much or at all the other properties of the pulsar that we see, which is much in relation with what I was explaining. No? This is the same by varying the meridional extent of the region. Let me not enter into these details unless you are later asking. Sorry, and then, so with this kind of modeling, now you can ask the following general question, global properties. How many observers see anything at all? Which is the number of light years with a given number of peaks? Which is the flux ratio between the two peaks, or the phase separation, or the width, which is the distribution of this quantity. And you can actually answer all of that with the simulated light years that you have in the model. More or less 40% of the observer will not see anything. This is relevant for population synthesis models of pulsars in gamma rays. But most interestingly, what we found is summarizing this slide. For instance, here I am showing you the number of light years with a given number of peaks. And in gray, you have the results in here for the second Fermi-Large catalog and the third Fermi-Large catalog, also in gray, but in darker gray, which is here. And then in color are for very different pulsars, which is the distribution of light years that we obtain from our own simulation for that particular pulsar. These pulsars could be millisecond or young. The period and the timing properties and all physical magnitudes could be very different, but all of them have the same distribution than what we observe, combining pulsars that have nothing to do. So the pulsar, the real pulsar catalog. So what we see essentially is that with one pulsar, you can actually explain the distribution of the observational features at the global level that we see. And the same happens when you consider the flux ratio between two peaks, the phase separation, or the width of the peaks. These are results of a single pulsar, and these are results of the observed population of pulsars, where you are mixing 300 pulsars, right? So essentially what I am saying is that when you build the catalog, you sample what they are, right? So if what they are is the same, and you simulate only one pulsar, then what you should obtain is the same as the catalog, which appears to be the case. So with this, I will conclude a couple of slides. Okay, so global observed statistics of the light years follow the same trend as that obtained from a single pulsar simulation when considering all the light years that this particular pulsar can produce. This agrees with all what I have said before, also from the observational point of view, in which the similarity is similar. No? And similarity, once quantized, shows that there are similar pulsars at very different timing properties or physical properties. What we are doing currently is individual concurrent fittings, one by one, of all the 3PC pulsars. We are developing for these fitting techniques because these are also not existing. And we are looking for correlations between geometry or geometrical parameters and physical parameters. And also we are studying the impact on the magnetospheric physics. And the pulsar similarity, actually any similarity, right? So any light year similarity, if you are using time series, and this may be useful also for you, can be phenomenologically quantified. This is new, and many light years in the 3PC look way more different than what they really are. This is something we have found. And okay, we introduced the DTW that contains several improvements in comparison with the Euclidean distance comparison, and of course with the eye of the beholder comparison, no? Which is what we were doing up to now. Clustering via light year similarity is now possible, and we can use that to compare physical and spectral properties of pulsars. This has a number of applications, even in gamma ray astronomy, that we are currently studying, but much beyond that. For instance, we can compare transitional pulsars, light years, and transitional pulsar candidates, light years, and try to see if they match each other with this methodology. We can compare magnetar flares, fast radio bursts, and gamma ray burst light years, try to see if some correlation or some groupings appear. We can also use this for single radio peaks, and all of this is, some of this is in the making, and others are in the thinking. one particular thing that is in the making, and this is very, very fresh, last week result, is that we are currently working on this transitional pulsar comparison. So what we want to achieve is a methodology that tells you how good is a particular system as a candidate for being a transitional pulsar. Because right now, what defined that something is a good candidate for a transitional pulsar is the light curve. But it's actually what we believe the light curve is similar to, because we just look, yes, it is very similar. It's kind of crazy, but it is like this. So we are trying to make this quantitative. And using the same methodology, we can compare the distances via dynamic time warping of things that we know are transitional pulsars, confirmed transitional pulsars, with the distance between confirmed and candidates of transitional pulsars. And the thing appears to be working, so we hope to be reporting on this at some point in the near future. So with that, thank you very much for your attention.
Okay, thanks, Diego. Nice talk. Very interesting. Questions?
Just to break the ice. Very nice talk from you. I wonder, I don't know if you explained, but I didn't catch it. These geometric figures in that appears the prismatic one and the other was having not sides. Are different steps in the
Like
comparison?
this? Like this? Or...
No, previously. There is this these groups, these ones. What is the difference between?
This is a cluster in which the lighters, as you see by eye, look very similar to one another, and they are identified. This is the graph showing only the edges that are beyond 3 sigma in the similarity parameter, and this is all the edges. And you see that all the other edges are between 2 and 3 sigma.
Oh.
So all the lighters are more than 2 sigma similar. I recall you that we have only a finite number of, we have 43,000 comparisons. So you do not expect to have 7 sigma here values, right? So, and this is the same, but with a different, I mean, here you have 2 peaks, here you have 1, and so on and so forth. You know? So it's like identifying. The issue is that when you go to the catalog here, it's impossible to identify this in the catalog. They look completely different.
That's really fun. Thank you.
I have a question. When you show the graphs, and I've seen a lot of graphs like this, do the shape means anything here? Yeah, the dimension. No. So this is basically just a representation of distance with your. It's a measure of distance, the correlation, similarity.
Yes, and also the distance between the two nodes also does not only the color means something, but not because there is no axis here. This is the point. So this is like in graph space. So this is graph here.
And it's the similarity index. If it's up above the threshold, you have the connection.
Exactly.
Have you analyzed these graphs in terms of connectivity, for example?
Not these ones, but we have been
change the threshold, for example.
Yeah.
Change the threshold, and then you might see regions showing up at some point.
Yes.
And below a certain threshold is just one.
Yes, we did. Actually, we are thinking of doing. Recall that last year we published several papers using graph theory to population, to the population of pulsars, to analyze the population. But in there, we only use timing magnitudes. So P dot and all the timing derived magnitudes. We have no similarity for the light years in that distance included. So one thing we will do is to use the same tools that we developed before, where all of what you are saying is already included for the pulsar similarity.
Question, I didn't see who.
Ignacio was there.
Really? seniority.
In which way is this, well, it was a very nice talk. In which way is this dynamical working method optimal? So would you think of other methods? So
it's better than the Euclidean distance for sure.
of course.
But it's certainly not the only thing you can do, let's say, from an advanced mathematical point of view, but on the comparison of light years. So I wouldn't say it is optimal, and certainly it is costly numerically. So I would not say this is the optimal thing to do. It's the easiest. I mean, the easiest up to certain threshold. Once you are above, is the easiest. But,
maybe computational.
yeah, it's yes.
Because it involves close neighbors.
Yes.
But other methods to compare, like if, I don't know, maybe you can take the Fourier transform or do cross correlation, but none of them stretches.
No, this is true.
So I don't know how. I think maybe it's close to optimal, if not optimal, because computationally not for sure.
Computational
But
is
as a way to measure similarity, however you define it, I think it's excellent.
is excellent. Yes.
Yeah, I mean, following up on this, and I understand that the claim is that the top rows there are similar likers, but I see striking differences in some of those, right? So especially the one on the bottom left is
This
very
one.
different,
It
and
is.
then the symmetries are also quite different in some cases
Yes.
on different sides, right?
Yeah.
So I understand there's a more complexity of this. Is there any plan to go one level in complexity and then study, for example, the shape of the better of the peaks, which seems to be changing even in similar cases, right?
I mean, two parts of the question. The second part is we realize that what you are saying, and now I'm coming to what you say, but we have not yet been smart enough to develop a plan, because you are asking, is there a plan? No, we don't have a plan, because we really don't know how to follow up on this at the level that you are requiring or you are implicitly requiring in the question. But we certainly realize, let me come back to the first part of the question, that for instance, this liker is very different from this, right? So, and that's good, because we see it from this perspective, right? So what is similarity? What makes a pulsar similar to one? This is not defined. So it's only that if you want to see two likers that look similar, then several of these do not look that similar to you, right? But this is not an estimator similarity. And then the idea is that what we can complement this study with is from theoretical analysis. Then we have all these likers simulated within a theoretical model that contains magnetoferrophysics, particle acceleration. And then we can start to complicate that model to start to see the inner structure that some likers have and some others don't have. But
and following up on this, you say that you don't find any correlations with any of the observables, let's say, or the intrinsic physics parameters of your clusters.
Except geometry.
Except geometry. Could it be because of this lack of some level of detail when this similarity?
Yes, exactly. We think so. At some point, I mean, what we are seeing here is just like the zero order approach. At some point, of course, geometry is the most important, and this will continue to be doing so. But at some point, the spectra of the pulsar has to have an influence, right? And how many particles are traveling backward in the magnetosphere or traveling forward in the magnetosphere will have an influence. So our model is our theoretical model is going to get complications in the following year, and actually in this year, in order to address partly some of these things. But from the second part of your question, only from the observational point of view, right now, it's difficult to figure out the next step, let's say, on how to complicate things further, because also the sample is not so large. at the end you have 300 pulsars. Not all of them are extremely well mapped. So right now we don't have this plan.
Good question. So these are in gamma rays, but you have these pulsars identified in radio, X-rays, other things. And do the pulsar shapes, and I mean, you also have pulsar shapes there, and probably much better measured radio. You probably have higher signal to noise and any repetition of cycles. Because here, probably you get these pulses after accumulating 70 years, like the radio telescope, 2 hours a day.
Yeah.
One at a time. So how these compare? Do you get also the double peaks? Are they the same peaks? Are they phase? At least they are not in the same position. That's information, right?
Yes, I will answer this question, but it's not directly related to the model or the similarity model that we are implementing. Because if you go to the third Fermi-Large catalog, you will see that for all cases in which we know the radio light curve, they are already there. So you can actually compare the gamma ray light curve with the radio light curve there, and they are mostly different. So the peaks are not at the same place. The number of peaks could be different. And this is understood because the radio emission is supposed to occur very close or much closer than the gamma ray emission to the surface of the star in the polar caps, whereas the gamma ray emission is happening further out, probably beyond the light signal. And the light curves are very different. From the point of view of the similarity estimation, yes, you can apply this to radio emission. We haven't done this because this is extremely new, but we have the chance to make this comparison. But it wouldn't make sense to compare radio against gamma ray emission because we are pretty much sure they are coming from different places.
Great talk, thank you. Do you propagate uncertainties in this method, or does that even matter? The flux uncertainty at every bin?
We don't do this systematically with every bin because the computational cost explodes. But we have done tests of what happens if you do, for instance, one case versus another or several cases versus another. And essentially what we see is that nothing changes because once you have a light curve that is very well described, let's say more than 100 bins, that means that the error bars of the flux are so small in comparison with the 0 to 1 that you are mapping, that even if you were to sample this, and we sampled this in a few cases, you get the same results. But we didn't do this for the 43,000 cases because it's computational.
My last question.
I have a curiosity.
Okay, wait.
Very quick. Now that you have all this data, well, extended in time and so on, did you find significant differences in the signal that is received from a same source over time?
Yes, there is variability. In some cases, it's very extreme, the variability, and this is also not completely understood.
Perhaps due to geometry as well?
Yes, in particular, the magnetospheric geometry could also change for a single source. This we see at some point already in the transitional pulsars, but not only, we have seen mode changes in pulsar that are interpreted as changes in the geometry, and in a few cases that are pulsars that are even isolated.
Okay, thanks. Diego again.
Thank you very much.
Please wait for the speaker. Ya no es de cuál, final.
Sí, sí.
Bien. Muy chulo, ¿eh? Lo de la